click record. Where is the record? There we go. Alright, so we're going to pick up where we left off before we went on to break. Let's do this. So we're talking about numerical integration. So let's go into writing mode. Okay, I don't want that one. Crap, I have like too many open. There we go. Yes, better. Okay, now the window is not, where did it go? There we go. Sweet. Okay, so we were talking about numerical integration. So we talked about how sometimes, look, there is no antiderivative. If there is no antiderivative, then you can't use the fundamental theorem of calculus. So what are you supposed to do then? So if you don't have any antiderivative, well, you're going to have to do the limit of a Riemann sum. Okay, and so what we were discussing last time was like, well, what's a better way that you can do your calculation as opposed to a Riemann sum? And the issue with the Riemann sum is that it over and underestimates. So like we have this little drawing right here. You can see that I'm going from x equals a to x equals b. You can see that like for the first, oops, oh, okay, wait, 1 second. My tablet's not working. What is going on? Okay, this is not working. There we go. Jesus. Okay, so for the first triangle, rectangle right here, you can see that it underestimates. For the second rectangle, it overestimates. For the third rectangle, it underestimates. For the fourth rectangle, it underestimates. Okay, now we could fix this by just, adding more rectangles. Okay, but the thing is, especially if you're trying to do this by hand, you would like the estimate to be more accurate more quickly. Like you don't want to have to wait for a bunch of, you don't want to have to like have thousands of rectangles or take the limit. Like what you want to be able to do is basically just not the limit of the Riemann sum, just take the Riemann sum, and preferably with as few rectangles as possible. So they, someone, I don't know exactly who, came up with the idea of the trapezoid rule. So instead of using rectangles, we use trapezoids for our estimates. So you can see the trapezoids right here. Right, so you have the same function in these two different graphs. Up here, you can see what happens if you estimate using rectangles. You can see that the rectangles are overestimates, 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 and then underestimates, like you're wrong by quite a bit. Now, so what are we going to do instead? Well, the things that we're going to estimate with are going to follow how the curve moves, right? So you can see that instead of drawing a rectangle, which would have been like this, instead what we have is a trapezoid that moves with the way that the curve flows, so you don't get any of this overestimate here, right? It's like following it really nicely. So what's nice about the trapezoid, instead of using a Riemann sum, what's nice about the trapezoid rule is that it ends up being pretty accurate with very few trapezoids, right? If you only were using 4 rectangles, your estimate for the definite integral might be very flawed. But with the 4 trapezoids, it's going to do a pretty good job of following it really nicely. Okay, so hopefully everyone can sort of see that. Okay, so we derived the trapezoid rule last time. We used the fact that the area of a trapezoid is 1/2 times its height times base 1 plus base 2. And we went through and we estimated it. And we found out that there's a rule for estimating area. So if you've got your function f of x and you want to find the area between x equals a and x equals b, you can partition this into n points. Right, so here's your x1, let's say here would be your x2, x0, x1, x2, x3, x4, x5, and this one would be x6. Okay, so you get your little trapezoids. So here we have 6 trapezoids that would like go something like this. Oh, Burrito's angry. Such an angry dog. So I'm drawing my 6 trapezoids. Oh, the last ones were not close, right? So it follows it really nicely. So how does this work? If you want to estimate this area, you're going to do 1/2 times delta x, and then you're going to have f of x naught plus 2 times f of x1 plus 2 times f of x2, all the way up to plus 2 times f of xn minus 1, and then plus f of xn. So what happens is you take your points, you plug your point in your first point and last point into the function, and then you plug every other single point in between, and you have to double those values. Okay, so we're going to do an example here in a moment. So I'll give you a moment to write down the formula. And what we're going to do is we're going to look and we're going to see how much more accurate the trapezoid rule is compared to a Riemann sum. Okay, so I'm going to do the example. Alright, so example. We are going to estimate the area under f of x equals square root x. Oops. Between x equals 0 and x equals 1, using n equals 4 with a Riemann sum and trapezoid rule. Yeah, let's see how much more accurate the trapezoid rule can be compared to the Riemann sum. Okay, so let's draw the picture of what we're dealing with here. Okay, so here's my x and y axis. Let's change that to white. Okay, and now we're dealing with square root of x. So square root of x looks something like this. Okay, and we're interested in going from x equals 0, which is right here, all the way over to x equals 1. Okay, and we're going to split it up into 4 parts. So I get x0 equals 0, x1 equals 1/4, x2 equals 1/2, x3 equals 3/4, x4 equals 1. Okay, right, those are the points. Shh. Those are the points on the x-axis. Okay, so we'll do the Riemann sum first. Okay, so for the Riemann sum, let's do right endpoints. You're going to get a rectangle like that. You're going to get a rectangle like this. rectangle like this, and a rectangle like that. Okay, so we're doing the sum where I equals 1 to 4 of f of xi times delta x. Right, so we can just factor out delta x. So what you get is delta x times f of x1 plus f of x2 plus f of x3 plus f of x4. Which in this case is just delta x times f of 1/4 plus f of 1/2 plus f of 3/4 plus f of 1. And Wolfram can help us out like calculating these numbers. So I'm going to open up a Wolfram and do that. Sorry. There we go. Stuff's in the way. Okay, so I'm just going to pause for a moment. Does everyone see what I'm doing? I've got my function. I already told you that we're going to be estimating it with 4 rectangles, right? So I wrote that down. I have my sigma notation right there. And then I expanded it, right? It's going to be f of x times delta x for those 4 different things. I decided to factor out my delta x. I guess we should actually write down what delta x is. Delta x is b minus a, which is 1 minus 0 over n, so 1/4. So I'm going to replace that with a 1/4 right there. Okay, so I'm going to transfer over to Mathematica now. Oh no. Burrito wants to go outside. Not now, Burrito. Leave me alone. Okay, there, I'm over to Mathematica. Okay, so let's just write what our function is. Our f of x is equal to square root x. Okay, now what I can do is I can use the sum function. So the sum function will sum things for me. So I want the sum of f of x, and you have to tell it what numbers you want it to plug in. So I'm gonna say I'm plugging in x values. I'm gonna start at 0. I'm gonna end at 1. Actually, I'm not starting at 0. I'm starting at 1/4. And I'm ending at 1. And we're plugging it in steps of 1/4. Oops. So like what this is here is it's actually plugging in the numbers. So the 3/2, that's f of 1/4. The 1 over root 2, that's f of 1/2. The root 3 over 2, that's f of 3/4. So let's make it go to 1.25. There we go. So there, what it's done there is actually it's added up. Does that make sense? What it's doing is it's plugging it in, like remember how the points, their delta x is 1/4, and I'm plugging in the right endpoints? Like there you can see there's the things that it's plugged in. It's plugging it into my square root function. So let's turn that into a decimal. If you plug in those 1, 2, 3, 4 points, you get 4.19 approximately. Okay, so let's go back to OneNote. So what we found out here is that this sum right there is approximately 4.19. Okay, and then we have the 1/4. So what's 1/4 of 4.19? Let me go back to Mathematica. So 1/4 times the 4.19 is 1.04779. Okay, so if you add these four rectangles up, you get an approximate area of 1.04779. Okay. Smoothing with it. What happened? I don't want that to happen. Okay, weird. Okay, what just happened? This is like stuck there. Weird. Sorry. It was like floating. Okay, there we go. Okay, so according to this, if you add up all these rectangles, it's 1.04779. Why did you calculate up to 1.25? Oh, because apparently, like, you're talking about on Wolfram, Matthew? Because apparently it doesn't plug in the last value. So if you tell it to go from 0 to 5 by 1, it will do f of 0 plus f of 1 plus f of 2 plus f of 3 plus f of 4. It won't plug in that last number 5. So if I'm going by quarters and I want to stop at 1, you have to tell it 1.25. It's really weird. I don't know why it does that. Creepy though, yes? Okay, everyone, what do we know about this estimate here? The 1.04779 in relation to the actual value. So let's quickly calculate what the 3 months on with 4 rectangles is. So we're integrating from 0 to 1 square root x, which is integrating 0 to 1 x to the 1/2. Okay, the antiderivative is going to be 2/3 of x to the 3/2. I think it included. Oh, okay, let's go back and look. So you're saying it might have given us the wrong thing. Okay, let me look into that. Okay, let me rerun it. Ooh. Okay, yeah, my bad. Okay, 1 second. I want to figure out why that didn't work as I thought it should. So when having trouble. Sorry. The way it's supposed to work is that if you want the sum where I equals some number a to be of f of xi, you write sum f of x, comma, curly bracket, x, the start value, the end value, and then the step value. We're starting at 1/4 and we're ending at 1. So that's what would go in there. Okay, so I changed it. Let me recalculate it. Make sure that it's actually doing it right. Okay, 1/4, let me plug them in, 1/2 just to check. 3/4 and 1. Okay, so when I plug those in, we get 3.0. Yeah, I did plug it in wrong. So this should be actually 3.07313. And then when you multiply 0.768. Okay, so now what we're going to do is we're going to compare that to the actual answer. So we're going to get 2/3 of, okay, you're going to get 1 to the 3/2 minus 0 to the 3/2. 1 to the 3/2 is just the actual area is 0.666 repeating. The actual area, and then this one is the estimated area. Okay, so 0.76, not too bad of an estimate of 0.66, right? Okay, and we'll see how much more accurate the trapezoid rule is in a moment. But we need to talk about the error that we encountered here. So there are two types of error. There is absolute error. Okay, I can't type. Absolute error. And then there's relative error. Okay, so the absolute error is the absolute value of the difference between the two numbers. Okay, so the actual area is 0.66 repeating. The estimated area was 0.768283. So if you subtract those two numbers and take the absolute value, what you get is, plugging it in, so the absolute error, the difference between what we were supposed to get and what the Riemann sum gave us, was 0.092 rounded. So that's the absolute error. So if someone told you that you are off by 0.092, that doesn't sound that bad, right? But the problem is that doesn't really tell the whole story. What you need to do is look at relative error. You need to take the absolute error and then divide it by the actual answer. So what we need is 0.666 repeating minus 0.768283, and then divide it by the actual area of 0.666 repeating. So if you do that, you get uh, 0.137, which is 13.7%. So in other words, even though the difference between the two numbers was small, it was only 0.09, there was a 13% difference between the area estimate from the rectangles and the actual area, right? So like all that, basically all that area that the rectangles went over, that was 13.7% larger than it should have been, right? It was that much bigger. Okay, so now we're going to do the same thing again, but now with Simpson's rule. Or not Simpson's rule, the trapezoid rule. So So let's copy this. Copy. Let's paste it down here. Oh my god, this is like so much easier. I can just like redraw the thing. I love this. Okay, so now instead of estimating it with the rectangle, we're going to estimate it with the trapezoids. So the trapezoids are going to estimate it like this. They have little lines. Oops. So now we're going to get it. It's going to follow it like so. Okay, so the trapezoid answer should be a lot. Does everyone see those like green highlights right there? Those are the tops of the trapezoids. Okay. Now the estimate for this is, what was the formula? Where did you go, formula? 1/2 of delta x times f of x0 plus 2f of x1 plus 2f of x2 plus 2f of x3 plus f of x4. So notice x0 and x4, those are the starting points and ending points right here. Right? I'm starting at 0 and I'm ending at 1. So what I'm going to get is 1/2 times 1/4 times f of 0 plus 2 times f of 1/4 plus 2 times f of 1/2 plus 2 times f of 3/4 plus f of 1. And it's really easy to enter that into Wolfram. Let's go back over to Wolfram. So I can just like literally type it in. It's like 1/2 times 1/4 times f of 0, because I defined what the function was, plus 2 times f of 1/4 plus 2 times f of 1/2 plus 2 times f of 3/4 plus f of 1 . Let's put in the multiplies. Okay, apparently, what does all that add up to? That, but let's turn it into a decimal. You get 0.643283. So let me switch the screen back. Okay, so all this becomes 0.643283, which is actually really close to the actual answer, right? It was supposed to be 0.666 repeating. So the absolute error between those two things is absolute error, which is the actual answer, 2/3, minus this. The difference between them is only 0.023. Okay, then what's the relative error? Well, now you need to divide that by 2/3, which I did in Mathematica. So the relative error is 0.035, which is 3.5%. Okay, so what does this mean? When you did the rectangles and you had all of that overestimate, so if you did the regular Riemann sum, it was off by 13.7%. But if you used trapezoids, which followed the square root, you were only off by 3.5%. Right, so that's actually a pretty dramatic increase. Like, what would you rather have? Like an error rate of 13% or an error rate of like 4%? Like the 4% is way better. It's like it's actually pretty close to what you want. And in fact, the trapezoid rule is basically always more accurate than the Riemann sum. Right? Does it make sense to everyone why it's more accurate and how I'm calculating the accuracy, which I'm calling the relative error? The amount that like it overestimates or underestimates by. I'm gonna pause. Yeah, sort of. I know it's a lot on the first day back. I'm gonna pause. Oh, like why you get those twos there? So if we go back up, I know we talked about it like over a week ago, but if you go through and you use the formula for a trapezoid, which is 1/2 of height times base 1 plus base 2, you get this thing AI equals 1/2 of delta x f of xi plus f of xi plus 1. Do you see that in blue? Okay, so if you start adding up all of those rectangles, what you notice is that for one of your formulas, let's say you plug in 0. When you plug in x equals or I equals 0, you're going to get f of x0 plus f of x1, right? And then if you plug in I equals 1, you're going to get f of x1 plus f of x2. And then if you plug in I equals 2, you're going to get f of x2 plus f of x3. So notice there was only one x0, but how many x1s were there? And how many x2s were there? So that's why after the first one you get doubles. Does that make more sense? And you get it from when you plug it into the formula. And we did that sort of last time here. You can sort of see how I plugged it in, right? F of x0, f of x1, f of x1, there's two of them. F of x2 and f of x2, you can see it highlighted in green. Yeah, the way I plugged it in, the relative error into Wolfram is just like a calculator. Let me go back. Okay, so like you see I have absolute value of 2/3. So here, where'd it go? Here. So okay, here I calculated the error. I'm sorry, here I calculated the area using the trapezoid rule. Boom, I got 0.64. So what I then did was to get the absolute error, I did the absolute value of 2/3, which is the real thing, minus, do you see this percent sign? Percent sign means the last number I calculated. The last number I calculated was the area, 0.64, so it did 2/3 minus 0.643283. The difference between those is 0.02333836. Okay, and then to get the absolute error, to get the relative error, I took my absolute error right here, and then I divided it by the other one. It's sort of like the answer button. Is everyone familiar with like the A and S key on a calculator? Like if you calculate something and then you want to do something that number, you press A and S and then like times 3. Like that's what the percent sign does in Wolfram. Here, let me show you. Here, let's say I do 5 plus 2. What does 5 plus 2 give me? 7. Now let's say I want to do something to that 7. I could just put $sign and then plus 3. See how it gives me 10 now? So I calculated 5 plus 2, it gave me 7. Now I took that 7 and I added 3 to it. Right? It's like the answer key on my calculators. Is that familiar to people? Have we used that feature before? It's really useful for calculating stuff. Okay. So the trapezoid rule ends up being quite, what's the word? More accurate than the Riemann sum. So let's talk about how accurate it can be. There's actually a way to figure out how wrong your estimation might be if you're using the trapezoid rule, which is pretty cool. And actually, there's also a rule that says how accurate your Riemann sum will be. So let's say that you're calculating a Riemann sum with n rectangles. So the error, whoa, my thing's like lagging. The error that you might get is going to be at worst m times b minus a cubed divided by 24n squared. So I'll explain what that is. Like, you have your function. There's your f of x. And you're estimating the area between a and b. So that's what the a and the b are. And you're doing it with n rectangles. So at worst, your Riemann sum is going to be b minus a, which is like the width of your interval, cubed, divided by 24n squared, where n is the number of rectangles you're using. And then m is equal to the maximum of the second derivative on the interval AB. So we'll calculate this for our previous example. So like for the square root example, we had our f of x was square root x, which is x to the 1/2. And we had 4 rectangles. Oops, I was writing where you can't see. We had f of x equals square root x, x equals x to the 1/2. Our n was 4, our a was 0, and our b was 1. So if we plug into the formula, we're going to get m, we'll deal with that later. 1 minus 0 to the 3rd divided by 24. The number of rectangles was 4, so we'll have 4 squared there. So we're going to get m times 1 cubed over 24 times 16, which will be m over, oh my god, what the hell is 24 times 16? Twenty-four times 16 is 384. So whatever m is divided by 384. Okay. So now we need to know the second derivative. Well, the first derivative is 2/3 x to the 3/2. Actually, shit, no. That's the integral. If you take the derivative of x to the 1/2, you're going to get 1/2 x to the minus 1/2. There we go. And then if you take the second derivative, you'll get minus 1/4 x to the minus 3/2, which if you redraw that, that's minus 1 over 4 square root of x to the third. Okay, so now we need to know what's the biggest that this thing can get between 0 and 1. Wolfram is really useful for this. So let me go to Wolfram. So what I'm going to do is plot this function. I'm going to see, like, well, what is minus 1 over 4 times the square root of x to the third look like between 0 and 1. So we're plotting it. And it looks... I think we can even ask for the maximum. Let's have Wolfram find the maximum for us. I think we can do that. Oh, okay, that's not working. Oh, okay, you can't do that. Well, looking at the graph, what's the biggest that it could definitely be? It's a negative value. It's monotonically increasing. So it attains its largest value at the right endpoint. So you can plug 1 into it, and you'll get that its largest value. Does it make sense that it's the biggest off at the right at x equals 1, looking at the graph? Oh, actually, oh, wait. So you want the largest absolute value. So at the end, it's equal to some number. It actually looks like it's biggest here at near 0 because it's asymptotic. Oh. 1 second. Let me look at this. If m is the maximum value of the second derivative. It is continuous. All right, one second. If m is the maximum value of that. It's not working. Because this doesn't have a maximum. What the hell? Yeah, you need to calculate the maximum and then take its or you want the maximum of the absolute value. The only problem is, let me go back over here. Well, if you look at, I can't annotate my screen. Okay, so I'll just change back to here. There we go. Okay, so this is our second derivative. Oops. This is our second derivative right here. And we're looking at this second derivative between 0 and 1. and we want the maximum of its absolute value. Now, what's the problem with this function? What happens to this function at 0? That's like making my example not work the way I wanted. Yeah, it goes to infinity. So like the maximum is infinity. So I'm looking at it, I'm like, okay, maybe this is just not a good example. We'll do another one. I think that's what we'll do here. Okay, so instead of doing the square root example, let me do it with a different example. Let me change how big my face is. My face is too big. It's like taking up too much real estate. There we go. Okay, let's say that you were estimating the area under x squared between 0 and 1 with 4 rectangles. Okay, so you would plug everything into this formula. Let's forget about the m for right now. You'd get 1 minus 0 cubed over 24 4 squared, which is m over the 384, just like we got before. Okay, now this one's more straightforward. If you start calculating the derivatives, the first derivative of x squared is 2x. What's the second derivative going to be? Just 2. Okay, so what's the biggest that the second derivative can get? What's the largest value my second derivative is capable of taking? 2, right? So you would just plug that in, and you would get 2 out of 384. And so if you calculate that as a decimal, that ends up being 0.005, which is 0.5%. Oh, actually, it's not a percentage, it's just a number, my bad. Okay, so what that means is that if you were to calculate the area under the curve of x squared between 0 and 1 with 4 rectangles, that's the most that your Riemann sum might be off by. Like, the answer that you got from your Riemann sum is going to be either at most that much smaller or that much bigger than the actual answer that you, like the actual area. Rectangles. So if you were to calculate the area under the curve x squared between 0 and 1 with 4 rectangles, this is how much you would be off by at most. So does it make sense this formula is here? Because it allows, you can like plug in numbers and you can say like, oh, how much am I going to be off by? And you look at this and you're like, oh, I'm only going to be off by 0.005. That's not that bad. Okay, now there's another formula to figure out the error if you're dealing with trapezoids. So if you're trying to estimate the area with n trapezoids, this is the formula you're going to use. M b minus a cubed over 12n squared. So let's say that we were estimating the area under x squared between 0 and 1 with 4 trapezoids. Well, you just start plugging into the formula. Let's figure out m later. 1 minus 0 cubed over 12 times 4 squared. That's just going to be m over 12 times 16. What the hell is 12 times 16? Twelve times 16 is 192. So you get m over 192. Now, for f of x equals x squared, we figured out that m is 2. So you get 2 over 192. So you go and you calculate, well, what is 2 over 192? And you get 0.0104. Oh. It should be more accurate. Usually it's more accurate. Sad. In this case, somehow the trapezoid rule ends up being less accurate. But it allows you to compare, like, which one should I use? You can, like, plug your numbers into the two formulas, and it gives you a good idea, like, oh, well, if I use this one, I can expect to be wrong by this much. If I use the other one, I'll expect to be wrong by that much. No, that's a good question, though. So, okay, let's talk about that. Let's say that your function you're saying is x cubed. Now, what's the interval over which you're estimating the area? Just give me your numbers. Just make something up. Because remember, you're always estimating an area. Okay, cool. So your first derivative is 3x squared. Your second derivative is 6x, right? So what you would do is you would graph your second derivative, 6x, and now what you need to do is figure out, well, what's the biggest 6x is between 1 and 2. Now, obviously, by looking at the graph of the function, what's the maximum value your second derivative has on the interval 1, 2, 12, so your m would be 12. So does that make sense? It wouldn't necessarily have an infinite. You care about the maximum of your second derivative on the interval that you're estimating. Yeah. And that was the problem with my first example, because you looked at the second derivative and it had an asymptote in the fucking in the interval we were working on. So I was looking at that and I was like, wait, okay, this is not going to work because it has an infinite second derivative, right? So it's not going to work well for us. Cool, cool, cool. I'm going to pause for a moment. How are we doing on time? Oh, crap, we're done.